Hello, yeah, there's a few more capacitor questions. So we start by defining capacitance. You should be getting pretty good at these definitions now. So capacitance, this is the charge stored per unit potential difference. So yeah, I'm not going to bother writing that one out. Part B, figure 1.1, we got a circuit with a resistor and a capacitor of 4.5 microfarads. Right, they've put that on there. Close switch 1, leave switch 2 open, so we're charging up the capacitor. PD across the capacitor is 6.3 volts. Calculate the charge stored. So Q equals CV. So we got 4.5 times 10 to the minus 6 multiplied by 6.3. So we want 4.5 6.3s. 4.5 sixes is 27. 4.5 0.3s is 1.35. So 28.35 times 10 to the minus 6, which is then going to be, well, 2.8 times 10 to the minus 5 coulombs. Energy stored by the capacitor. So we want a half QV is probably going to be, or well, that's the same as half CV squared. So we've got CV, so we want to take that answer and then we want to multiply it by, E is equal to a half multiplied by V multiplied by our, well, this answer that we've just got here, 2.835 times 10 to the minus 5. Right, actually I'm going to, I think I will go for the calculator on that one. And that comes out at 8.9 times 10 to the minus 5 joules for two significant figures. Right, so a couple of easy starter calculations. Now you open up switch 1, close switch 2, so we're going to discharge. Describe and explain in terms of the movement of electrons how the potential difference across the capacitor changes. Right, I mean, it's useful to say which direction things are going in. So we've got on this initial setup, so this is positive, that's negative. So we're going to end up getting positive there, negative there. So we're going to get electrons flowing anti-clockwise. So the electrons flow anti-clockwise, which means that what am I trying to do here? So movement, how the potential difference changes. Right, okay, I've distracted myself a bit. So you could say this, so we've got the electrons flow anti-clockwise, so leaving the lower plate slash depositing on upper plate, and this means that the magnitude of charge on each plate decreases. Magnitude of charge on each plate decreases, therefore the PD decreases exponentially. So yeah, that gets a lot of ticks there. Then, oh, that was that bit. Right, the energy stored in the capacitor decreases to 0. State where the initial energy stored on the capacitor is dissipated. Right, well, all these electrons are having to do work somewhere. If we've got ideal wires, the work's being done in the resistor. So this is going to be work done in resistor. So we could just say, well, it's like heat. Yeah, that's what it's going to be. I mean, it doesn't actually say why, it just says where. So resistor is the key thing that we want really on that bit. Is that the end of the question? Nope, we got another bit. Right, part D, figure 1.2. Oh, they've replaced the resistor with another capacitor. So we've stuck a 1.5 microfarad capacitor in. Right, okay, so we close the switch, we charge up the 4.5 microfarad capacitor as before, then we close it, open switch 1, close switch 2. Right, calculate the total capacitance of the circuit when S2 is closed. Right, well, that's easy enough. We're just adding the two of them together. So we're going to get, not 66.0 microfarads, just add in the 4.5 and the 1.5. Calculate the final potential difference across the capacitors. So we've got that the charge is conserved because we know here, this is our So that's our positive, our negative. The electrons are going off there. We've got positive, negative. So we've got all these electrons here, which are going to equalize. All these electrons that we've built up on this bottom plate here, some of them are going to whip round and we're going to equalize. So we've got the same PD across each capacitor. So yeah, some of the charge will move across, but the charge is conserved. So we've got the same amount of charge, but we've got a new capacitance on all of this. So we've got our voltage is equal to the charge divided by the capacitance. So if we want to get the final potential difference on this, we've got the same Q. So we're now going to 4.5 over 6.0 multiplied by our initial voltage, because the charge is exactly the same. As in, what I'm doing there is saying, okay, Q is equal to CV. These are the same. So we've got our first capacitance, 4.5 multiplied by 6.3, is equal to our new capacitance, which is 6, multiplied by our new voltage. So I'm just taking that 6 down there to get what the new potential difference is. So we've got 3/4 of 6.3. What's 3/4 of 6.3 going to be? We're going to have 4.5 plus a sort of 2.25-ish. So it's going to be about 4.7 volts for 2 significant figures. If you want more significant figures, then go to the calculator. Okay, so that wasn't too bad. All right, next up. Figure 1.1 shows the circuit. We've got a capacitor, an ammeter, a variable resistor. Close the switch. The resistance of the variable resistor is adjusted to keep the current in the circuit constant. Right, they like these sort of things. Explain in terms of movement of electrons how the capacitor plates X and Y acquire an equal but opposite charge. Right, a number of times they asked this. So it's another one that you should be getting familiar with. So we've got electrons being deposited on plate Y, removed from plate X because the electrons are flowing anti-clockwise in this circuit diagram. You've got the same current throughout the circuit, so equal and opposite charge on each plate. So they're all of the key points that you want to say in all of that. But I've gone through that one quite a few times before, and I'm sure it will come up again. Initial charge on the capacitor is 0. After 100 seconds, the PD across the capacitor is 1.6 volts. Constant current of 40 microamps. Right, to calculate the capacitance C of the capacitor. Right, so we've got a Q is equal to CV, which is also equal to I times T. This is what we're putting together. We want to get the capacitance. So our capacitance is going to be equal to I, which is 40 times 10 to the minus 6 multiplied by T. What was that? 100 seconds. Divided by our 1.6. So that's 40 over 16 times 10 to the minus 3. So that's 2.5, isn't it? 40 over 16. 2.5 times 10 to the minus 3 farads. That's our capacitance. On figure 1.2, sketch a graph to show the variation of potential difference V across the capacitor with time. Right, okay, so how is the potential difference changing with time? Right, well, we've got we had this here, so we've rearranged this equation up here. So, right, V is equal to I divided by C multiplied by T. But they have also told us that I and C are constants because they've kept it at constant current. So that means we've got V is proportional to T. We've got a straight line through the origin with gradient I over C. We also need to go through, 100 seconds, 1.6 volts. So we need to get to about there with a straight line through the origin. So that was nice. That'd probably catch out quite a few people, that one, because they'll probably start doing those sort of things, charging up capacitor exponential curve. But yeah, we got constant current, so that changes matters. Part B shows an arrangement used to determine the speed of a bullet. Wow, okay. So we've got a resistor, value of the resistance of the resistor, and value of the capacitance of the capacitor are shown. Right, okay. Voltmeter reading is initially 6 volts. Cool. We've got 6 volts there initially. That's our V0. Bullet first breaks the circuit at A. Right, so that stops the capacitor from charging. Then it will start discharging. So it will start discharging exponentially through the resistor, and then it goes through that and it stops the discharge. Right, okay, so we've dropped from 6 volts to 4 volts. Calculate the time taken for the bullet to travel from A to B. Right, okay, that's interesting. So we want then our time constant. This is going to be useful because we're going to have to start doing our exponential decay stuff. So our time constant, C times R, so that's just 4.7 multiplied by 220, and then we've got this 10 to the minus 6 in there as well. So that is equal to 4.7 multiplied by 2 1/5 times 10 to the minus 4. So yeah, 2 1/5 on this. So that's going to be 9.4 plus 1, 10.4, and then take away 0.06. So that's going to be 10.34. So let's go 1.034 times 10 to the minus 3 seconds. Right, so that's given us our time constant. Now we need to go to our V equals V0 e to the minus t over CR. And we know what V and V0 are because V is 4 and V0 is 6. So we can say that 6 over 4 is equal to e to the t over CR. I'll just flip them both over in order to get rid of the minus sign. So what am I trying to work out? The time taken. So t is going to be equal to CR multiplied by log 3 over 2. Well, we've worked out CR there. I'm going to go to the calculator with that one. And that comes out at 4.2 times 10 to the minus 4 seconds to significant figures. Right. Separation between A and B is 0.1 meters. Calculate the speed of the bullet. So our speed of the bullet is going to be, well, we want to do our separation divided by the time, distance over time, 4.2, and then we're going to have a 10 to the 4 on there. So that comes out, well, I've got the calculator on now, so I might as well keep using it, 238.5, which is 240 meters per second to significant figures. Right, that's another really nice question. So yeah, they kind of ramp these ones up. So I'll leave that there because this has been quite a long video already. I've got another batch coming up in a moment.